On space science, the journey always begins where mystery meets reality. Have humans really discovered something terrifying on the far side of the moon? Or has the truth been hidden in plain sight all along? Beyond the face of the moon that Earth always sees lies a silent world of deeper craters, ancient scars, and one of the most violent records in the solar system. What astronauts saw, and what later missions confirmed, reveals a place far stranger than myth, and far more unsettling than fiction. Before we begin, please like the video, subscribe to Space Science, and turn on notifications so more calm. Fascinating space documentaries can keep coming. Now, let the far side of the moon slowly reveal what it has been hiding for billions of years. Between Earth and the moon, space appears open and simple, yet it is not empty in any ordinary sense. It is a region shaped by distance, motion, sunlight, and radiation. It contains no air to carry sound, no weather to soften light, and no horizon except the curved edges of two worlds separated by a long interval of darkness. From Earth, the moon seems close enough to belong to the same sky in an intimate way. It rises over trees, buildings, deserts, and seas. It changes shape from night to night. It casts pale shadows on quiet ground. But once the journey begins, the familiar brightness of the moon gives way to scale. The space between the two bodies stretches to an average distance of about 384,000 kilometers. This is near enough for a spacecraft to arrive within days, yet far enough that Earth begins to loosen its visual and emotional hold. As a vehicle moves outward from Earth, the planet does not vanish at once. It remains large in the windows, wrapped in cloud, ocean, and reflected light. White storm bands turn slowly over blue water. Brown and green land masses drift under the thin brightness of the atmosphere. That atmosphere, so slight from a distance, marks a profound boundary. Below it lies pressure, weather, breathable air, and the familiar exchange of heat and sound. Above it begins a very different environment, one that does not support life and does not adjust itself to living needs. Space does not resist gently. It offers no cushion, no medium, and no protection. It simply remains what it is, a near vacuum through which matter travels without the ordinary comforts of a world. In this region, sunlight behaves with unusual clarity. On Earth, air scatters light and fills shadows with a soft glow. Between Earth and the moon, there is no such veil. Illumination falls sharply on surfaces facing the sun, while shaded areas turn dark with little transition between the two. A spacecraft crossing this distance passes through strong light and deep shadow as it rolls or changes orientation. Metal can heat quickly where sunlight falls and cool quickly where it does not. Thermal control becomes essential, not because space is cold in a simple way, but because heat enters and leaves through radiation alone. Without air, there is no breeze to carry warmth away and no blanket of atmosphere to hold energy in place. Every surface must manage its exposure with care. The journey also alters the meaning of speed. On Earth, motion is often judged by the landscape sliding past. In open space, there is no road, no nearby marker, and no sound of wind. A spacecraft may travel at many thousands of kilometers per hour while seeming almost still from within. The cabin contains its own small order of objects, instruments, restraints, and human bodies moving carefully in weightlessness. Beyond the walls, the vehicle follows a path governed by gravity and initial momentum. It is not pushing through a substance. It is falling in a controlled way through curved space under the influence of Earth, then increasingly under the influence of the moon. This kind of motion can feel calm while remaining exact. A small error at departure can grow into a large error over great distance. As Earth recedes, communication remains possible, but distance introduces delay. Radio signals travel at the speed of light, which is very fast. Yet even light requires more than a second to cross the gap one way. A message sent from near the moon takes roughly 1¼ seconds to arrive at Earth, and a reply takes the same amount of time to return. The delay is short compared with the age of worlds, but it is long enough to change conversation, judgment, and the rhythm of support. Immediate exchange gives way to a measured pause. In this widening corridor between Earth and Moon, every instruction and every report moves with that fixed lag. The effect is subtle, but real. Distance begins to enter human action, not only as geography, but as time. Radiation is another steady feature of this passage. Earth's magnetic field and atmosphere provide important shielding at the surface and in low orbit. Farther out, that protection weakens. The space between Earth and the Moon contains a background of energetic particles from the Sun and from beyond the solar system. These particles are too small to see and too fast to sense directly, yet they matter deeply. Over time they can damage cells and electronics. Their intensity varies. At quiet times the radiation environment is more stable, though never absent. During strong solar activity, the hazard can rise significantly. For this reason, mission planning depends not only on engines and trajectories, but also on weather of a very different kind, the changing activity of the Sun. Observations indicate that short lunar missions can limit exposure to acceptable ranges with proper shielding and timing, but the environment remains harsher than the one near Earth. Weightlessness shapes the human experience of the crossing. In common speech, this state is often called zero gravity, though gravity is still present throughout the journey. The spacecraft and everything inside it are falling together, so objects do not rest on floors in the usual way. Bodies drift. Tools must be secured. Movement becomes deliberate and efficient. The inner ear, accustomed to the steady pull of Earth, can react poorly at first. Some astronauts experience disorientation or nausea. Over time, the body adapts, but adaptation does not remove the strangeness. Simple acts such as eating, sleeping, and turning around require method. This is not drama. It is routine in an environment where the usual cues of up and down are absent. The view outward grows quieter as the vehicle advances. Earth shrinks, the Moon expands. The stars, if visible outside the glare of sunlight, do not twinkle because there is no atmosphere to disturb their light. They remain hard and steady. Their stillness can make the human craft seem smaller than any ordinary measure allows. Between two natural bodies, separated by hundreds of thousands of kilometers, the spacecraft is a brief manufactured presence, carrying warmth, breath, and intention through a region indifferent to all three. This contrast defines the passage. Inside are metabolism, memory, checklists, and controlled systems. Outside are vacuum, radiation, and long geometry. Even the simple idea of rescue changes here. In low Earth orbit, a mission remains near the planet. Around the Moon, distance slows response and narrows options. Equipment must work largely as intended. Crews must solve immediate problems with what they carry. The space between Earth and Moon is not an abyss in a poetic sense. It is a measurable operational gap, yet its practical effect can feel severe. Consumables are finite, trajectories are constrained, return windows matter. A failure in this region does not become meaningful because it is mysterious. It becomes meaningful because it is remote. By the time the Moon begins to dominate the view, the crossing itself has already made one fact plain. The far side of the moon is not first defined by what lies on its surface. It is first defined by the long separation required to reach the body at all, before rock, dust, or crater enters the account. There is transit through open space. There is the leaving of one protected world and the movement toward another that has no air, no sea, no living surface, and no natural refuge. The journey is calm in appearance, quiet in motion, and exact in its demands. In that calm lies the first part of the moon's severity, not as fantasy, but as distance, exposure, and the slow reduction of Earth to a bright sphere behind the travelling craft. The moon travels around Earth in a steady path, and during that movement it keeps one hemisphere generally turned toward its larger companion. This pattern creates one of the most familiar appearances in the night sky. The near side, with its dark plains and bright highlands, is the face seen from Earth without the aid of spacecraft. The far side, by contrast, remains hidden from direct ground view. Hidden does not mean permanently dark. It does not mean sealed away from sunlight. It means only that this hemisphere does not usually face Earth. The distinction is simple in geometry and powerful in imagination. Much of the old mystery of the far side begins in this ordinary but exact arrangement of motion. This arrangement is called tidal locking. A tide, in the broad physical sense, is a stretching effect caused by gravity. Earth's gravity pulls on the moon with slightly different strength across the moon's width. Over long spans of time, this uneven pull influences the moon's rotation. Early in its history, the moon likely spins more quickly relative to its orbit. But the constant gravitational interaction between the two bodies slowly changes that state. Internal friction within the moon, produced as its shape responds very slightly to Earth's pull, dissipates energy as heat over immense time. This process slows the rotation until the moon takes about the same time to spin once on its axis as it takes to orbit Earth once. When those periods match, the same hemisphere remains pointed toward Earth most of the time. The result is often misunderstood in simple ways. It can seem, from everyday language, as if the moon does not rotate at all. In fact, it does rotate. If it did not rotate, all sides would come into view from Earth during the course of an orbit. Instead, the moon turns at just the right rate to keep the same general face toward Earth. A useful image is that of a walker circling a central point while always facing inward. The walker must turn gradually during the circuit. In the same way, the moon rotates once during one orbit. This is not a rare coincidence in the solar system. Tidal locking appears elsewhere as well, especially among smaller bodies orbiting larger ones at close range. It is a natural outcome of a long gravitational interaction. Even so, Earth does not see exactly half of the moon and never more. The actual pattern is slightly richer. Because the moon's orbit is not a perfect circle, because its axis is tilted a little, and because the observing point on Earth shifts as the planet rotates. Small changes occur in what becomes visible along the edges. These gentle apparent nods and sways are called librations. A libration is an apparent rocking motion that allows observers over time to glimpse somewhat beyond the average boundary between near and far hemispheres. With careful observation across many nights, people on Earth can see about 59% of the lunar surface, not only 50%. Yet this does not remove the far side from its hidden character. It only means that narrow outer margins come into view under favourable conditions, while the deep interior of the far hemisphere remains beyond direct sight from Earth. For most of human history, this unseen hemisphere exists as a blank in practical knowledge. People know the moon changes phase. They know it rises and sets. They track eclipses and mark time by its motion, but the hidden half remains inaccessible to direct inspection. No mountain range on Earth offers a better view. No clearer atmosphere reveals it. The barrier is not sharpness of eyesight. The barrier is orbital geometry. A full understanding requires leaving Earth entirely. Only when spacecraft move beyond the Moon or around it can the far side be seen directly. This historical fact gives the far side a particular kind of weight. It is not merely distant. It is structurally withheld by the mechanics of the Earth-Moon system. The far side is therefore a consequence of relationship. It exists as the hidden hemisphere because the Moon's history with Earth locks its motion into this enduring pattern. The same gravitational bond that stabilizes the familiar lunar face also conceals the opposite one. This bond is old, likely established early after the Moon's formation, and refined over hundreds of millions of years. By the time human observers begin careful astronomy, the arrangement is already ancient. The Moon has been showing one face and withholding the other for longer than complex life has existed on land on Earth. The calm of that repetition can make it feel timeless. Yet the Moon is not perfectly still in a deeper mechanical sense. Its orbit carries it around Earth approximately once every month relative to the stars, relative to the cycle of phases, which depends on the changing angle between Earth, Moon, and Sun. The period is slightly longer. These overlapping rhythms shape what observers see from Earth, but they do not alter the basic locked condition. New moon, first quarter, full moon, and last quarter are changes in illumination, not changes in which hemisphere faces Earth. The far side experiences the same cycle of day and night as the near side, though at opposite times in relation to Earth's view. When the near side is fully illuminated during a full moon, the far side lies in lunar night. When the near side is dark at new moon, the far side is in day. This is why the common phrase dark side is inaccurate when used to describe the far side. Darkness there is temporary, not permanent. This clarification matters because language can quietly mislead. A hidden hemisphere is not automatically a strange one in physical law. It obeys the same celestial mechanics as the near side. It receives the same sunlight, though on a different schedule. It travels through the same orbital path. What differs is visibility from Earth. That limited visibility, however, has consequences for how people imagine it. When a region cannot be seen directly, imagination tends to rush in and fill the absence. Stories, fears, and inventions often gather in such places. The far side has carried that burden for generations. Science gradually replaces absence with measurement, but it does so slowly, beginning with orbital understanding before surface detail arrives. From space, the locked relation becomes easier to grasp. A spacecraft approaching the Moon sees no magical dividing line between near and far. The boundary is simply the turning of a sphere. As the craft changes position, new terrain rotates into view and familiar terrain slips away. What remains constant is the underlying rhythm, one body orbiting another. Rotation matched to revolution, geometry preserved through time. This quiet precision is what holds the far side beyond Earth's direct gaze. It is not secrecy in any active sense. It is the stable result of ancient gravitational tuning. Thus the hidden hemisphere begins not as a landscape but as a motion. Before craters, mountains, or rock chemistry enter the account, there is the locked dance itself. The Moon circles Earth and turns once in each circuit. Earthbound observers receive the same general face again and again, century after century, while the other hemisphere remains out of view except for slight-edge glimpses granted by libration. In that repeated turning lies the foundation of the far side's character. Its remoteness is written first in orbital mechanics, in the slow and exact agreement between spin and path, and in the long habit of a world that always offers one face while keeping the other beyond the line of direct sight. When a spacecraft moves behind the moon as seen from Earth, a practical silence begins. This silence is not a failure of instruments and not a change in the behavior of radio waves themselves. It is the simple result of solid rock standing in the way. Radio signals, like visible light, travel very effectively through empty space, but they do not pass easily through the bulk of the moon. The moon becomes a barrier between transmitter and receiver. A spacecraft on the far side cannot send a direct signal to Earth because the line of sight is broken. In orbital flight, this interruption is expected, timed, and understood with precision, yet its effect remains striking. For a period, the craft and crew, if crew were present, would pass out of immediate contact with the world that launched them. This condition depends on geometry rather than distance alone. A signal can travel from the moon to Earth in a little over a second when the path is open. The problem begins when the moon itself blocks that path. Communication in space usually depends on line of sight, meaning an unobstructed straight route between antennas. If a planet, moon, or other solid body lies between them, the signal is cut off or weakened beyond practical use. Around the far side of the moon, this is not a rare disturbance but a built-in feature of the environment. Every orbit that carries a spacecraft behind the lunar globe creates a communication blackout unless some form of relay is present. During the Apollo missions, crews orbiting the moon pass repeatedly into this radio shadow. Each time the spacecraft goes behind the lunar limb, meaning the curved edge of the moon as seen from the approach line, contact with Earth ends. Mission controllers know the timing in advance. The loss of signal is normal. Then, after a measured interval, the spacecraft emerges and contact returns. The pattern is orderly. But within the silence, Earth cannot speak to the crew and the crew cannot speak to Earth. Telemetry, meaning the steady flow of engineering data sent from the spacecraft, also stops during that period. Heart rates, cabin values, voice reports, and guidance updates all disappear from direct view until line of sight is restored. The silence is often described in emotional terms because it removes one of the strongest links between a spacecraft and home. Yet in technical terms it is a manageable constraint. Mission design accounts for it carefully. Crews receive procedures before entry into lunar occultation, a term meaning blockage by the moon. Spacecraft systems are expected to operate autonomously for the duration. Navigation, attitude control, power regulation, and life support cannot depend on continuous ground intervention. This requirement increases the importance of onboard reliability and crew discipline. The far side does not become dangerous because it emits something unusual. It becomes severe because it briefly denies immediate support. For robotic missions, the same problem appears without the human voice, but not without consequence. A lander placed on the far side cannot communicate directly with Earth at all if it remains fixed on the surface. The moon's body blocks the signal continuously. To solve this, a relay spacecraft must be placed where it can see both Earth and the far side mission at the same time. One useful location is an orbit around the moon designed for repeated visibility. Another is a region near the Earth-Moon system called a Lagrange point, where gravity and orbital motion allow a spacecraft to maintain a relatively favorable position. A Lagrange point is a place in space where the pulls of two large bodies and the motion of a smaller object combine in a stable or semi-stable balance. From such a location, a relay can act as an intermediary, receiving signals from the far side and forwarding them to Earth. This solution has been used in real exploration, China's Chang'e 4 mission, the first soft landing on the far side of the moon, depends on a relay satellite named Kuekiao. The relay is positioned so that it can maintain communication between Earth and the lander rover system on the lunar far side. Without that link, commands could not be sent in useful time and scientific data could not be returned. The mission demonstrates that the far side is accessible to instruments and machines. But not in isolation. Communication there requires architecture. It requires another spacecraft placed in just the right region to bridge the blocked view. The radio shadow also gives the far side a rare scientific quality. Because Earth's transmissions do not reach it directly, the far side is shielded from much of the radio noise produced by human technology. On Earth, and in near-Earth space, radio astronomy must contend with countless artificial signals from communication systems, radar, broadcasting, and electronic activity. The lunar far side offers a quieter environment, especially for low-frequency radio observations that are difficult or impossible to make from Earth's surface because of atmospheric effects and widespread interference. This does not mean the region is perfectly silent in every physical sense. Solar activity and cosmic sources still produce radio emission, but it does mean the far side is unusually protected from Earth's persistent electronic brightness. That protection has led scientists to consider the far side as a valuable place for future radio observatories. Such observatories could study early cosmic history, solar activity, and other phenomena using frequencies badly obscured or contaminated near Earth. The idea is practical and scientifically strong, though difficult. Any far-side observatory would face the same communication problem as any lander there. Data return, time synchronization, and operational control would all require relay support. The very quiet that makes the location attractive also makes it logistically demanding. For human explorers, a long stay on the far side would deepen these demands. Short communication delays caused by distance would remain, but the larger issue would still be obstruction. Without a network of orbiters or relay stations, a base on the far side would disappear from direct contact whenever the moon stood between it and Earth, which would be always for a fixed location. Daily life in such a place would therefore depend on systems designed to tolerate interrupted command, delayed maintenance support, and local decision-making. This does not make the far side unknowable. It makes it operationally independent in a way the near side is not. The silence behind the moon has another quality that is harder to measure. Spaceflight often depends psychologically on conversation, status reports, and the simple fact of being heard. A spacecraft that slips behind the moon enters a period where the crew, if present, continues moving, working, and observing without the immediate echo of Earth. The machines remain active, the cabin remains lit, checklists continue, and the moon turns below. But the usual stream of voices is absent. In that absence, the far side acquires part of its enduring character. It is not only hidden from view, it is separated in communication. This separation is exact, repeatable, and rooted in physical law. The moon blocks direct radio contact just as it blocks ordinary sight. Relay systems can bridge the gap, and careful planning can manage the blackout. But the underlying fact remains unchanged. The far side is a place where direct connection to Earth is not naturally available. Any signal must wait for geometry to change or for another spacecraft to carry it onward. In this way, the moon's hidden hemisphere is defined not only by what Earth cannot see, but by what Earth cannot hear without help. The radio shadow is calm, measurable, and temporary in orbit, yet it reveals a deeper truth about the far side. It is a region where isolation is built into the landscape before any footstep, instrument, or wheel ever touches the ground. Light on the far side of the moon arrives without air, without cloud, and without any softening layer between the sun and stone. It falls directly onto the surface and leaves every shadow with a hard edge. This is one of the first conditions that shapes the far side as a real place rather than an imagined one. The landscape does not glow gently. It alternates between brilliant illumination and deep darkness according to the angle of the sun, the tilt of the ground, and the long rhythm of lunar day and night. Because the moon rotates slowly relative to the sun, one full cycle of daylight and darkness at a given place lasts about 1 lunar month. Daylight continues for roughly 2 Earth weeks, and night follows for roughly 2 Earth weeks, on the far side as on the near side. This long cycle governs temperature, visibility, and the basic physical behavior of the uppermost surface. The phrase far side can sometimes invite the mistaken thought that this hemisphere is permanently dark. It is not. When the near side faces Earth in darkness at new moon, the far side lies in broad daylight, when the near side shines full and bright in Earth's sky. The far side is in night. The two hemispheres share the same solar rhythm, offset by the moon's locked relationship with Earth. Sunlight therefore remains the main source of change across the far side surface. It determines when rock warms, when dust cools, when crater floors brighten, and when long ridges cast black, extended shadows across old terrain. Nothing in this sequence is dramatic in a sudden way. The changes are slow, exact, and relentless. Because there is no atmosphere, there is no dawn in the earthly sense. On Earth, sunrise begins before the sun itself appears. The sky brightens as air scatters incoming light. Colour spreads across cloud and horizon. On the moon, there is no such gradual filling of the sky. The sky remains black even in full day. Sunlight reaches the surface directly, and brightness builds only where the sun actually touches the land. The horizon line stays stark. A low sun can send light almost sideways across the ground, making small ridges, stones, and crater rims stand out with great sharpness. Under these conditions, relief becomes very visible. Tiny changes in height create long shadows. Texture announces itself through contrast rather than colour. This sharp lighting has practical importance for observation. Features that seem flat under a high sun can become easier to read when the sun is low. Crater rims, ejecta patterns, and rough fields of broken rock reveal their form through shadow length. At the same time, very dark shadowed regions can conceal detail almost completely. Since there is no air to scatter light into them, they remain deeply black unless lit by reflection from nearby ground. Astronauts in orbit around the moon describe this contrast as severe. Cameras and human eyes must adjust carefully. A bright sunlit slope and a shaded crater interior can differ so strongly in apparent brightness that both cannot be seen equally well at once. On the far side, where the terrain contains many old craters and elevated highlands, this pattern of stark illumination shapes first impressions of the whole hemisphere. Temperature follows the same slow cycle of exposure. During lunar day, surface temperatures in sunlit regions can rise well above the boiling point of water at Earth sea level pressure, though liquid water cannot exist there in ordinary surface conditions because there is essentially no atmospheric pressure. During lunar night, temperatures can fall to extremely low values, well below -100 degrees Celsius. The exact temperature depends on the surface material, slope, latitude, and whether sunlight has fallen recently. Fine dust warms and cools differently from solid rock, and sloped crater walls may hold or lose heat at different rates depending on their orientation. Since there is no air to move heat around, Each patch of ground responds mainly to radiation and its own thermal properties. The surface becomes a mosaic of local thermal behavior within a larger cycle of day and night. This long exposure to intense sunlight and deep cold affects the uppermost rock over time. Repeated heating and cooling can contribute to the breakdown of exposed material, though impacts remain the dominant force shaping lunar soil. Thermal stress, meaning the strain caused when material expands in warmth and contracts in cold, can open cracks and weaken rock surfaces over many cycles. On the Moon, this process is slow, but over very long spans it adds to the grinding effect of micrometeorite impacts and particle bombardment from space. Light is therefore not only a means of seeing the far side, it participates, indirectly, in altering the ground. At high latitudes, the angle of sunlight becomes especially important. Near the lunar poles, the sun remains low over the horizon even during local day. This creates regions of long shadow and, in some places, areas that may never receive direct sunlight at all. Such permanently shadowed regions are more strongly associated with the polar environment than with the far side as a whole. But some parts of the far side near the South Polar region share in these conditions. In such places, temperatures can remain extremely low for very long periods. Observations indicate that water ice may survive in some of these permanently shadowed regions, mixed with the surface material. The details of distribution, concentration, and accessibility remain active subjects of research, but the role of light is central. Where sunlight never reaches, cold can persist over geological time. Away from the poles, the far-side highlands present another visual effect. They're generally brighter than the dark basalt plains that dominate large parts of the near side. Basalt is a volcanic rock formed from cooled lava, usually darker because of its mineral content. The far side has less extensive basalt flooding across its visible broad surface, so much of it appears pale by comparison. Under direct sunlight, this brighter crust reflects more light, seen from orbit. The far side often gives an impression of rough, light-toned terrain covered by craters of many sizes. Under high sun, some of that roughness can appear washed in brightness. Under low sun, the same region becomes a field of edges and shadow. The absence of atmospheric scattering also changes the sense of distance. On Earth, haze makes remote objects softer and bluer. On the Moon, distant features can remain optically hard if they are illuminated, though actual visibility depends on local topography and the observer's position. A mountain or crater rim at the horizon does not fade through air. It drops instead into the blackness of the sky or into the curvature of the ground. This can make the landscape feel at once near and immense. Surfaces seem carved with unusual precision. The eye receives form without the usual veil of atmosphere, yet scale is difficult because familiar cues are missing. When spacecraft orbit above the far side, the movement of light across the surface becomes a major guide to interpretation. Sun angle can reveal or conceal geologic structure. Night removes the visible surface almost entirely except where instruments sense heat or reflected light from another source. In day, brightness can look almost harsh. In shadow, detail can vanish. The far side is therefore a place where illumination does not merely reveal the terrain. It governs how the terrain exists to sight at all, its long day, long night, hard-edged brightness, and